All right, welcome back to your 3 practice problems here. Hopefully you've already tried this, so you realize that question 2 is calculator active, so you've got whatever graphing calculator available for you. Yeah, hopefully the Inspire downloaded on your computer, or the 84 on your computer, or an actual calculator, or worst case scenario, you can always use Desmos. So let's get to problem 1 first. Write but do not solve an integral, and this is actually really common. Because of that square, it turns out that finding antiderivatives of things that are squared can be pretty tricky, so a lot of them are right but don't solve, which means less work for you, so you should be excited to see one of these. An integral to find the volume of the solid generated when r is revolved around the horizontal line y equals 6. Okay, so here's my line of revolution, give or take. So I'm going to spin this friendly shape around this line. So first thing I'm going to do is say, well, let's see, 0, 6, this is all exciting. I don't even know what that function is. That's fine. This is a little gap here, so I've got maybe the rest of my axis here. Here's that same gap. This comes all the way up and over. Let's just do it here. So something like that. That's pretty close. That doesn't have to be perfect. Okay, and we've got that shape. Great. Okay, and then we need to spin said shape, and when it spins, we're going to make very friendly, cute little circles here. So here's my first one, here's another one, we'll do a third one just for good measure. That's pretty decent. Impress your friends with your 3-dimensional skills. This kind of looks like almost a volcano, right? Volcano, yeah, solid volcano all the way through. Okay, so then we need to go ahead and find our volume. So we have our circle first, and with this circle, we know, of course, the area of a circle is pi r squared. So my area function is going to have to be pi times something squared. So the question becomes, how do we find the radius? Well, let's look at these different radii here. You could draw the radius from top to middle every single time, but the problem is, to find the length of this changing radius, you need to know the equation for the top function and the bottom function. The bottom function we do know. The bottom function is the line y equals 6, but we don't know the top function, so I'm actually not going to use that as my radius this time, and instead I'm going to go ahead and use the radius that's down below. Right? That's still a radius, and the advantage of using this lower radius is I know both of these functions. Notice the top function is y equals 6, and the bottom function is this function over here, y equals 4 ln of 3 minus x. So now we have both functions, top minus bottom, so we're using a radius that looks like this here. And so my top function being 6, always good to put it in parentheses, bottom function being 4 ln of 3 minus x, and I think we should be set there. There's my formula for the area of a circle. Now realize, and this is good news again for you, that because this is squared, if you switch these two, technically your radius is negative, but then you square it and it becomes positive anyway, so you would still get the right answer and you'd still get full points, but you should really strive to do it correctly, which would mean get a positive radius instead of a negative one, top minus bottom. Alright, second thing we need to do is we need to create our volume function. My volume function takes this and it gives each of these circles a little bit of depth, this third dimension here, that is again going to be along the x-axis. That's going to be our dx, and for this third dimension, it's going to turn these circles into disks, and the disk, of course, is going to be the same here, pi 6 minus 4 ln of 3 minus x squared, and then the third dimension is the dx. Last but not least, we need an integral. Nothing too bad. We need to sum up all of these circles here, and just rewriting quickly, I don't know why I put an extra 4 there, 4 ln of 3 minus x, too many parentheses, squared, from what to what? Well, we start summing up our disks at 0, we stop summing up at 2, 0 to 2, let's make that a 0, not a 6, and we're done. So again, these problems really are not too bad. You just need to draw a circle and give us the area of a circle. It's just a modified version of this cross section. The cross section just happens to go through your paper instead of popping out at you. Alright, let's move on. Problem 2. Two areas here, we're taking S. What are we doing with S? S is revolved around the x-axis to create a solid. So I'm going to extend my x-axis down here. Hopefully better than that. It's going to look something that's about the same length there. This point's going to come down here. There's a little like loop. That's going to be a little bit longer down like that, sure. And then this one has got to come around like that. Okay, that's my piece like that. And then we need to go through and do some cool little circles here. So this one's going to be a little bit weirder, but this is going to get spun like that. This one's going to get spun here. And this one's going to, I'm going to change colors for a reason we'll talk about in a second. That's going to get spun there, and then this one's going to get spun over there. Okay, so we've got all these fun circles here, but what we really need to realize is that we have two different functions controlling the radii. My first function, if you think about top minus bottom, is going to be whatever function this is. That looks exponential to me. I bet that's going to be our 2 to the x function. It's calculator active. You can double check for sure, but here's my 2 to the x function. That's going to control the radius of my blue circles. However, once we get to whatever this point is, and we're going to have to find this point eventually, but whenever we get to that point, and I'm going to give more space, it's probably going to be gross numbers, then we get over to a second function. I'll do the second function in yellow. This looks like an upside down parabola to me. This is probably my negative x squared plus 3. Okay, negative downward facing parabola shifted up 3, and now this one controls the radii for these other circles. So I think we'll probably need two integrals here, two area functions, however you want to think about it. So let's do my blue circle first, and that's going to be, and I'll try to write, how do I want to do this? Let's do it like this, and then I'll write underneath. So my area function, it's always going to be a circle. We have a radius that I'm doing in green, top minus bottom. My top function is 2 to the x, so we have pi times the radius squared. 2 to the x is the top function here, and the bottom function is the x-axis, which is 0. That's nice. Okay, maybe I'll call this a sub 1 of x, my first area function. My second area function, I did the circles in red. I'm probably going to run out of room, but that's fine. And we have a yellow radius here. My yellow radius, and again, we're going to, we'll do it in this color. My second area function is going to be pi times something. I've got room. Why am I doing that? Pi times something squared. And my top function now is the yellow one, which is going to be, careful with those parentheses, 3 minus x squared. The bottom function is 0. Alright, then we need two volume functions. Now I imagine we can see our volume function. We're just going to give our disk a little bit of width here, give this disk, or give this circle some width so it becomes a disk. Okay, and we're doing alright there. That looks good. I imagine we know that we could just put in a dx. So let's skip right to the integration. I need to integrate or sum up my first area function, which is going to be pi times 2 to the x squared dx, volume, right? And then I need to add on all the disks added up on my second area function, which is going to be pi 3 minus x squared squared dx. And from where to where? Well, my first one starts at 0 and goes to, this is where we need that point, so we'll get back to there in a second. And then the second one is going to go from that point over to whatever this is, and I already lost it, or maybe it's not even there. Oh, that's just the parabola, though. We could do that math. We could just set our parabola equal to 0. X squared equals 3, x equals plus minus square root of 3. Oh, that's nice and easy. We can just write the square root of 3 here. Okay. Now, this point, I'm going to be, well, not lazy, we're going to be efficient here, and I'm going to write this point as a. So I know I need the x value here. That's going to be a equals something, right? So let's get to it. We need to graph these functions, which I won't say I've cheated here, I've just prepared here. I've already graphed both of them, and I'm going to go ahead and find their intersection point. So menu, analyze graph, intersection, and it looks like I'm going to go somewhere in the middle here. Yeah, and then, nope, you stop that. Oh, that's a nice intersection point, 1, 2. That makes sense. If you plug in 1 here, you get 2. You plug in 1, you get 2. Okay, well, that's easy. Cool, I don't even need that a then, but I already wrote a, so I'm just going to do a is 1 and erase this and say, I don't know, b is 2. They intersect at 1, 2. Good for me. So we end up with those two, but then it said actually find the volume of the solid. So let's get to it. Let's let's see, I think we'll need my calculator here. We'll need a couple integrals. There we go. Menu, calculus, integral, and we need to go from 0 to 1 of, and don't forget your pi is hiding down here, so you have your pi times 2 to the x squared, which is great, and then we've got our dx, oh my gosh, dx right here, that's looking pretty good. And then we can go to the right, plus, and then we need a second one. So menu, calculus, integral. Whew, this is much slower typing on a tablet, but that's all right. So we end up with our square root of 3, and we're doing, let's try not to forget all the different components here. You've got your papers, that makes it pretty easy. I'm doing this on the fly, and I think it was 3 minus x squared, close your parenthesis, squared, pi r squared, excellent, dx, and enter. Whew, and there's our answer. Of course, that's our exact answer. My calculator is a CAS one, it's able to do that. So I'm going to copy this down and then do control approximately and get the decimal, and it looks like 10.2978. So I've got 10.2978. Whew, and we're good. Alright, yeah, that was a weird one. It had disks that were made by two different functions, but let's get on to our last problem. Last one. Alright, we've been rotating our regions about horizontal lines, but of course when we did cross sections we could go perpendicular to the y-axis, so it shouldn't shock you that we can revolve this around the y-axis as well. So let R be the region in the first quadrant bounded by all this stuff as shown in the figure to the right. Oops, nope, not to the right. This is the figure below because I see it down there. Haha. Write but do not evaluate an integral that gives the volume of the solid generated when R is rotated about the y-axis. Okay. So, same thing, but now instead of spinning it around the x-axis, we've got to spin around the y. Same idea though. I'm going to take the function, reflect it over here-ish, give or take. We're going to take this piece and scoop it up like that. It's pretty decent. And then we've got to give it 3 dimensions. So we're going to spin like that, spin like that, and then this last one is going to spin, it's got to be tight, like that. There we go. Okay, so this kind of looks like an inverted top, right? I don't know, kind of like a tornado twister that comes to a point the other way. So either way, that's looking pretty good. So let's start setting up our integral up here. Okay, I just want to be able to see my shape at the same time, so that's why I zoomed out. Same thing as before. We have a circle. We need to figure out what's going to make the radius. So going back down here, there's lots of options for the radius. We could do this radius, right? We could do this as a radius. Doesn't really matter. We could even go out, but that's really weird, so we're not going to do that. Disadvantage of going this way, we know our middle function, that's 0, but I don't know the equation for this one over here. However, I do know both of these equations. So I think this is going to be my radius going from the center out to the right side. So let's go ahead and build our area function. My area function here is going to be, again, pi times the radius squared. Okay, well, couple things, and I'm going to skip one step ahead. When I give this some width, notice that my width here is no longer along the x-axis. This width is on the y-axis. So this width right here is going to be dy, infinitely small, stacking upwards, right, on the y-axis, which means in my integral at the very end, right, when I integrate everything here, not sure why that came out to be green, when I integrate everything here at the very end, I'm going to have a dy, which means every single variable in my area function, my volume function, needs to be in terms of y. And so, if we look up at our equations currently are in terms of x. That's not super useful. Well, one of them is useful. That is our y-axis is x equals 0. It's x equals, that's good, but my other equation's not. So I'm going to need a little bit of space here. We'll just do it over here. Y equals 2 square roots of x. I'm going to go ahead and get x by itself. So I'm going to multiply by 1/2. And then square both sides. When you square everything on the left side, you'll get 1/4 y squared. There we go. Okay, so now everything's in terms of y. That's useful. This means this equation, although you could say it's y equals 2 square roots of x, you could also say it's x equals 1/4 y squared, same function, though technically that one would go down here too, but that won't matter for us. So we need to do our, instead of top minus bottom, right minus left. My right function here is that 1/4 y squared, and my left function looks like it's the y-axis, which is of course x equals 0. And cleaning this up again for when we do the volume, our volume is going to have that dy in here, pi times 1/4 y squared squared dy. That's going to give us, if we know a y value, the volume of one of these disks, but we want to stack up, think of them sitting on top of each other, we want to stack up all of these disks, so that's going to give me pi times 1/4 y squared squared inside of an integral from where to where? Well, we start stacking at a y, and I always like to put this so I don't forget a y of 0, and we stop stacking, here's the point over here, which one of these is a y? That's the 6, at a y of 6. Nice. And we're done. They just asked us to set it up, I think, right? They didn't actually ask us to solve here, right, but do not evaluate. Cool. We could have evaluated this, square everything, antiderivative, but it sounds gross, so we're not doing it. Now, I give you a bonus question. I'm not going to give you the answer here, but I'll at least give you the setup, and you could check these on your calculator if you wanted. Note when you plug this into your calculator, you don't have to use y, you can use x. Y is fine. Any variable is fine. So, bonus. Is the volume more, less, or equal to the volume of the solid which would be created if the region R was rotated about the horizontal line y equals 6. So it's easier for me to erase than you, so take a look at what I mean here. So I'm saying we created that one three-dimensional shape. What if you made a second one that looked like this, and then you did the circles this way? My question is, which one would have more volume? And it's actually more of a logic problem. You might be able to figure it out without doing any math, but to check yourself, actually figure out how you would find the volume, put them both into your calculator and see which one's right. Maybe they're the same volume. So think about it, try it, let me know what you get, right? You can include it as part of your assignment if you want. You don't have to do it, but it's a nice little brain teaser. So thanks for sticking with me and getting our three-dimensional drawings done. We only have one more day of learning and then we get to our review. All right.